Okay, welcome everybody. Really excited to have you here. My name is Ryan Abernathy. I'm the CEO and co-founder of Earthmover, and I'm coming to you from our office here in New York City. This is the first of what is going to be a sort of recurring open demo for our platform. The idea here is just to, and let more folks in on what we're doing, answer your questions, get your feedback, and yeah, just have a conversation with all of you about our platform. A lot of folks know our work on open source, but I think less people are familiar with what we are offering in Earthmover at the platform level. So excited to share with you. I'm gonna give a few slides here. And then I'm going to just jump into a live interactive demo, and I don't think we'll take much more than half an hour here. Cool. So to start, just a little bit about Earthmover. We are a startup. We are what's called a public benefit corporation. We're a mission-driven company, and that mission is to empower people to use scientific data to solve, excuse me, humanity's greatest challenges. So the company was founded by myself and Joe Hammond, and we really kind of spun out of the open source scientific Python Pangeo community. So Joe and I met while working together on Xarray, a very popular data analysis library in Python. And we also both spent most of our careers as, practicing scientists. Joe as a hydrologist, myself as an oceanographer. And experience firsthand, the challenges of working with Earth system data at scale. That's really what motivated us to start the company, to build tools that would help everyone working in the Earth system and scientific data space go faster, do more creative and innovative things, and ultimately solve the challenging problems that we are facing as a planet through better use of data. So our customers at Earthmover are companies that are building scientific data products. I think this is a useful way to describe, who our platform is useful for and perhaps who it's not useful for, right? And so a data product is, we characterize this as a specialized curated data set which drives unique business or organizational value. So to give some examples, Sarah is a company that rates carbon credits. And they do that by building this big database of global forest carbon by synthesizing multiple different satellite remote sensing data products. This database is sort of the core of how they provide those carbon ratings, and they store that data in our platform. Kettle underwrites property insurance, specifically focused on wildfire, and they have an amazingly sophisticated probabilistic wildfire risk estimate that incorporates a lot of different data sources as well as sophisticated AI methods. And again, that produces a data product that they use to drive their underwriting decisions, and they use our platform to manage that. RWE is an AI is an energy operator and trader, and they are developing AI weather forecasts for energy trading, and they are using our platform to manage and query that data to support their operations, right? And so this is a good filter if you're asking yourself, is this platform useful for you? Are you building a data product? And who our platform is not necessarily useful for are folks who just want to process some data on the fly, not really hold on to any data, not build up any sort of database, but rather just do some ephemeral calculations, right? There's a lot of great tools out there for that purpose, but probably not our platform. So, what are some of the typical challenges that these sort of teams face in building data products? There's a lot of them, but I've tried to boil it down to three high-level points. First one we call the data swamp phenomenon. I think everyone doing this wants to have a nice, clean, pristine data lake of the relevant data sources, inputs, the refined data that they are using in this process. But in reality, what ends up happening is teams develop a zoo of different formats, storage locations, data owners, technologies, and this phenomenon really limits the ability to collaborate, innovate, reuse data, ultimately slowing down the development velocity of that team. And I certainly experienced this during my time as a professor at Columbia, where we would have, we had a half a dozen different students and postdocs, and everyone had their own data stored somewhere different, and in different formats, and we couldn't really use it from one project to the other. And I was surprised to see that pattern persists throughout industry as well, teams struggling with the same sort of challenges. Another big challenge we hear about a lot is just basic performance. If you're doing advanced data science and AI, ML, you care about things being fast. And a lot of workflows we observe are just simply limited by I/O, by the ability to read and write data efficiently, particularly in a cloud context. This is where we see the toll of archival file formats being uploaded to the cloud, and folks struggling to really get high performance I/O on top of that data. Then finally, this is perhaps the most important piece. In order for these data products to have an impact, they have to be delivered to some sort of end users. So at our customers, those end users can be internal. It can be, a data science team producing data for another team, a product team or a sales team, or those can be external to the company, a team that's actually building data and selling it to commercially to other users, or perhaps in a more of a research context, a lab that's producing data and providing that to the public as part of their mission, as part of their mandate, right? Delivering data to end users can be extremely fragmented across different formats, different types of APIs, different data pipelines. And this slows down the rate of iteration and feedback between the data provider and the data user, which is a very important feedback loop to optimize, particularly in a commercial context. And so, these are the three big problems that we're thinking about when we look at solving data infrastructure challenges with our platform. So this is what our solution looks like. So this is our sort of architecture diagram. And I'm going to dig into what each of these components mean in some further slides and in my demo itself. So starting at the bottom here, our platform is designed to run on top of commodity cloud object storage. At Earthmover, we believe that cloud object storage is really the future infrastructure foundation for all data systems. And so we embrace that, and our platform works with Google Cloud Storage, AWS S3, Azure, and any S3 compatible object store, including those that are self-hosted, on-prem. As long as it's on the internet, it can be connected to our platform and used within this architecture. That object storage can be managed by us on your behalf, or it can be your own object storage in your own cloud. So if for many of our customers care deeply about data sovereignty and keeping the data living in their own cloud buckets, and that is certainly possible and common with our architecture. Now, sitting on top of this is a very important open source layer called IceChunk, which I'll talk a little bit more about in the next slide. But IceChunk provides the on-disk format for all of the data in our platform. And so you can think of IceChunk as a souped up flavor of ZAR that provides some other important features, database style transactions, versioning, etc. The point here being, while you're using our platform, you're building up IceChunk data in your cloud object storage. And If you start on this platform and then choose some future date to migrate away, you're still always left with that open format, open source data in your own storage location. We know that concerns about vendor dependency and lock-in are very important to our customers, and so we've designed this architecture specifically to mitigate that risk, make it easy for you to use this platform without worrying about you're not going to be able to get your data back in the future if you no longer want to be our customer. So that's part of the architecture. Everything within this purple line is our platform. And it consists of two main layers. Array Lake is our data management and data governance layer. And it provides a data catalog of these ice chunk data sets. It allows you to implement data governance by deciding who within your organization is able to see which data, read, write, and administer your ice chunk repositories. And then it provides a growing number of data optimization operations, automatically performing data exploration and garbage collection, cleaning up unused and unneeded data from your ice chunk repositories, and going forward into the future, recompressing, rechunking, reformatting that data in order to optimize it for compute. Now, you can connect directly to the Array Lake data using all of your favorite Python libraries. So we've built this layer of the platform to connect directly with ZAR, Xarray, and the whole Python data science ecosystem that we have spent our careers working in and contributing to. And so this is a mode of access that is appropriate for data scientists and AI, ML workloads, anyone comfortable using Python. But thinking about that data delivery piece and that need to send data to users in all kinds of different formats and different applications, many of whom may not be comfortable using Python and writing data science code. This is why we developed Flux. So Flux we can think of as an API gateway that serves up that same data in a variety of geospatial API protocols. And so this allows you to connect your data stored in Array Lake into all kinds of web GIS, desktop GIS applications, different, just about any programming language, spreadsheets, databases, you name it. This is really an interoperability that makes it really easy for that data to flow into different locations. This is the basic architecture, and when I jump into the demo, you'll see how all these pieces sort of play together. So we are really building this company with what we call an open core model, okay? Earthmover is the leading contributor to Xarray and ZAR Python. These are two libraries that we have been working on since before the company started, and we continue to play a leadership role in today. And then we've also recently open sourced IceChunk as another core open source project that is a key part of our platform. And so a lot of the value that we provide comes through these open source libraries. Xarray provides really the toolkit for data analysis. ZAR defines the storage format. And then IceChunk provides a sort of transactional layer on top of ZAR data that provides a lot more sort of robustness, safety, and performance when working with ZAR data in the cloud. And finally, there's another library that's a key part of this called XPublish that we use under the hood in Flux in order to deliver some of those APIs, which is also an option for self-hosting. So when you're our platform customer, you get all of the above. Those are all tools that we work on. And you get Array Lake and Flux. So Array Lake providing this turnkey data storage and management layer for your scientific data, including the data catalog, Python client, data governance capabilities, which includes some sophisticated credential management capabilities. And then Flux, the high performance gateway into your data, high performance fully managed service that handles authentication, observability, logging, providing data through standards compliant APIs in a auto-scaling, cloud-native, performant way. Just one more word about Ice Chunk. Sorry, I skipped a slide here. So Ice Chunk is a key component of this architecture. And if you're new to this ecosystem, really excited to share Ice Chunk with you. So Ice Chunk is you can think of it as like a database for Czar. It provides some database style features such as ACID transactions for robust, safe concurrent updates, data version control, and it also includes the ability to create virtual data sets layered on top of NetCDF, GRIB files, etc. And it works with, seamlessly within the existing ecosystem of Xarray, Virtualizar. It's written in Rust, and so that's where we get a lot of the high performance from Ice Chunk. So here's an example of what Ice Chunk enabled through a pilot with NASA. We compared using Ice Chunk with their existing solution for extracting time series from the GPM iMerge precipitation dataset that is stored, spread across hourly NetCDF file granules. And so we use the virtualization capabilities of Ice Chunk to layer new query patterns on top of the existing data. And we were able to massively accelerate the rate that we could extract a time series from that data without having to duplicate any data, copy any bytes over, without any caching or any other tricks. And so we're really excited about the performance we get from Ice Chunk, and you'll see some of this in the demo today. Okay, so thanks for listening to me go through these slides. And now I'm going to jump into the actual demo. The goal of this demo is just to demonstrate very simply the end-to-end user experience with the Earthmover platform using some ECMWF weather forecast data. We're going to start with just an overview of the Array Lake data catalog, sort of click through, show what the interface looks like and how we manage data. Then we're going to do some basic data ingestion. We're going to start with some raw GRIB files. ECMWF forecast GRIB files, ingest those into Array Lake, and then query them back with Python. If you're already familiar with Xarray, that part will look very familiar. And then finally, we're going to look at Flux and how we can access the same data over different APIs, including WMS for making interactive web maps, interacting with desktop GIS applications, and EDR for exporting JSON, CSV, Parquet, or NetCDF files. Okay, so I am now going to stop sharing, and I am going to move over to my demo. Here we go. Okay, so I am now going to share this window. All right. So when you log into our platform, what you see is the main Array Lake dashboard, which is telling us how much data our organization is storing and how it's spread out. So you can think of our application as modeled, our data, our high-level sort of entity model, roughly modeled after GitHub. GitHub, you organize your data into organizations, and then those organizations have repositories. And it's the same in Array Lake. If you sign up for our platform, you get your own organization. This organization here is called Earthmover Demos. And then this organization has got a bunch of different repositories, which I'll show you in a second, which is where the data actually lives. These are not Git repositories, though. These are Ice Chunk repositories. We can see a little bit of a graph of how our storage has been growing over time. You see we have some data ingestion running that's growing the volume of data under management in this org. Just going to click through some of the interface to show how some things work in here. So these are the 5 different cloud object storage buckets that are attached to this organization. So we can see we've got some buckets in Google. Google Cloud. We've got some S3 buckets. I think we have some other cloud providers and some different orgs. But the point here is this is a multi-cloud solution. You can attach many different cloud storage providers to your organization and manage them all through one interface. We've got a sort of user management console, so we can define different roles for our users from a basic member all the way to an admin and various levels of granularity in between. We can create new members. We can edit their permissions within our organization. We can create API clients. So these are like tokens that you can use to access Array Lake in a machine-to-machine fashion from an automated script or job or web application. So all of the sort of standard features you'd expect from a data platform. We've got our services. So these are these Flux-based APIs. We've got WMS, EDR, and DAP all running. And we can interact with these. We can look at the logs. We can start and stop them, etc. And then we can also see some logs from those in our dashboard here. We can see the how our services are being used when data is being queried. So we have a lot of observability over the usage of our data. Okay, so now let's get into the data itself. We'll go dig in on one of these repositories. So I'll just click on this one for now. This is a demo I was working on yesterday for a customer who was interested in hyperspectral data. So we ingested some hyperspectral data into the platform from the company Wyvern. And here we can see the core entity. This one has kind of a weird name, but the core entity here is the multidimensional array, right? And so we've browsed into one of these arrays. We can see its dimensionality. We can see its shape. We can see its chunking. So this is ZAR data. And that's what the platform manages. And so these repositories here are just ZAR stores that are versioned and tracked through the IceChunk library. So at this point, I'm going to switch over into a Python notebook and show the process of actually ingesting data into one of these repositories. So I'm going to move over here. I'm going to start running some Python code in a notebook. Is my text big enough? Does anyone want me to zoom in and make this bigger, or can you see my code well enough? I see a thumbs up. See a hand raised. Okay, a lot of thumbs up, no thumbs down. I'm going to carry on unless someone speaks up. Okay, so here is the basic user experience of using our platform from Python. So we're importing Array Lake and we're creating a client library, a client object, which is what talks to the Earthmover platform. And here I'm going to run this line, create repo. I've created a repo called Earthmover demos /ECMWF-IFS opera. So this is a name of the forecast data set that I'm going to ingest. And so what happened is the platform has created an IceChunk repository in the default storage location. It's created credentials for us to access that resource. And now we've got an IceChunk repository that we can interact with and we can write data to. Okay, here we've got some code to ingest ECMWF forecast data this is some data that's already stored in S3. You don't need to understand every line here. The important parts are, this is GRIB data. So we've got forecasts that are stored as one GRIB file per forecast step. And so we've got a few functions that figure out what those URLs should be and get the forecast for a single step, make some tweaks, open it with Xarray, ultimately returning an Xarray data set. And so the details here aren't super important. What's important is that anything you can open with Xarray can be ingested into the platform. So I'm going to run this function. I'm going to define some a forecast date and some hours, specific forecast times that I want to ingest. And then I'm just going to start a thread pool, which is going to download these files concurrently and bring them onto this machine, and then I'll be able to open them up with Xarray. This starts slow and then speeds up and finishes in a minute or two. At least it does, in all past demos. But of course, you know how it works with live demos. They always love to trip you up. Okay, so this is running, and we are getting our GRIB files downloaded. And I guess this is just an important point to highlight the value of cloud optimized data. It's a lot easier to when we're starting with these individual GRIB files. That is a slow process to access those files, whereas if we have cloud optimized data in ZAR and IceChunk format, it's really trivial to open up our data set. So now that we've downloaded those data sets, we can open them up in Xarray. And this is one forecast that we are going to ingest into our platform. Okay, and so we'll do that in the following code. We will create a new session in IceChunk. So you can think of this as like a transaction context in which we will perform this ingestion. And this is kind of a key point. With IceChunk, any update happens in the context of one of these transactions that then has to be committed. If you don't commit the transaction, no one can ever see the changes that you make. And no other users of the data will ever see in progress updates or incomplete or fragmented data. They'll only see a committed snapshot. And you, as the person ingesting the data, get to decide when you're going to make that call commit here. And this is a sort of way of sealing those updates or changes. Familiar idea from Git, if you've used Git before, but maybe new in the context of data management. So now that we've done this right here, we can go over back to the web app, and we can see the data that we've just ingested. And so what's happening here is the web application is actually connecting to the data in object storage, reading the IceChunk data, and showing it to us in a nice web interface. And so here we can see total precipitation rate, one of the variables that we've ingested. We can see we've got some, it's chunked. We've got metadata in here. And we can also see a full history of the data that we have created. And this is an important and novel component of this technology. We can see when the repository was initialized. We can see when the data was written. If we make further updates, appending more data, adding new forecasts, modifying stuff, we'll see full set of track changes here. We can see all the changes that were made along the way. We can see, all these arrays that were created and how many chunks, individual chunks were written. So that's the ingestion process. Obviously, I just ingested a small amount of data, but for larger data sets, we will scale out this ingestion over big clusters, ingest, terabytes and terabytes of forecast data. It all scales quite well. Now I'm going to show perhaps the most simple and obvious way of interacting with the data. I'm going to open it up with Python. And so here I'm just calling Xarray's OpenZAR method on the same repo that I just wrote to. And I'm pulling up that same forecast data set. Rather than having to download 100 GRIB files, instead I'm opening up a single analysis ready object. It's essentially instantaneous to open this data. If I want to query it for a specific forecast step and make a map that is trivial, I can pull it out and make a map using Xarray syntax. I can also pull out a time series of my forecast just as easily because we've chosen a nice balanced chunking scheme that allows multiple different query patterns to work well. And that's, I think what a lot of users of Xarray are used to and expect. But here we have this integrated really seamlessly with the Earthmover backend. So what I'm going to show next is how we interact with this data from Flux. So Flux is the API layer that serves up the same exact data over different protocols. And so in this cell here, I'm going to create a leaflet web map of the forecast data I just ingested. And so here I'm connecting to this backend, specifying a URL. I'm using the WMS or Web Map Service protocol in order to query the data. And this is pulling data directly from that ice chunk data in object storage through the Flux gateway right into my browser, as if these were static map tiles, but instead they're being served dynamically from live data. And so you can see we're pulling that data on demand, and satisfying those tile requests really quickly. And this way we're able to have an interactive web map pointing at our ZAR data in cloud object storage. There's a lot of tweaks we could make here. We can change the style. If you like a different map style, you can change the color map. There's a lot of options that are available here. So that's a very simple WMS demo. Later, I'm going to show you a web app that uses this in a more sophisticated way. Next, I just wanted to show EDR. So EDR is a protocol for extracting areas of interest from gridded data at locations or within bounding boxes, and returning the data in various formats, including JSON, CSV, NetCDF, Parquet, etc. So here we're pointing at the same data, the data we've just ingested, ECMWF IFS Opera, and we're just specifying a point coordinate, a time that we want to extract, a parameter name, and a format, CSV. And we can run this cell, and we will just pull this out in CSV format and open it up with pandas. And here we've got our weather forecast, in a very easily digestible format, CSV, that's accessible to basically any type of data user in the world. We can plot that up if we want to see it's just the same data. So here I've used these APIs in the context of just another Jupyter notebook, which is really just for demo purposes. If you're in Jupyter, you're running Python, you might as well just go direct using Xarray anyway. But where these APIs really shine is when you're building an interactive web app. So last week we had a demo where we showed an app like this one, where we're using these APIs to build a really beautiful visualization of weather data, and then an ability to click on any point within this map and pull out a time series of the forecast, and then download that in any number of different formats, JSON, CSV, GeoJSON, Parquet, or NetCDF. And so this is using the same APIs under the hood, but in the context of a interactive web-based JavaScript application. And I think I'm going to close this because it almost completely freezes my computer when I try and use that and have Google Meet going at the same time. The last thing I'm going to show you here is just pulling the same data into a spreadsheet. So we know spreadsheets are the sort of universal, most democratizing data technology in the world. And here we are just hitting one of those URLs directly and using an import data command in Google Sheets in order to just pull that CSV data straight into our spreadsheet and make a plot of it in Excel. Well, Google Sheets, same thing. And so this is just showing, once you land your data in this platform, it's just really easy to have it interoperate with all kinds of downstream data systems. Okay, so that is the end of my demo. I'm just going to pop back up the slides, and I'm going to just show you what I just showed you. I'm going to put that summary back on, and would love to answer any questions folks have.
Hey, thanks for the demo. Looks great. Just a quick question about the data loading itself in the leaflet, the visualization in the leaflet. Is that can we load data larger than the memory of the machine you are showing the visualization, because the computation happens on the Array Lake in the cloud, right? So you can basically
Yes,
zoom in
absolutely.
and then you see the original resolution. But okay, yeah, okay. So that's a
Yes,
scalable part. Okay.
Exactly. Nothing about that is running locally. And I'll actually show you a quick architecture diagram that explains how this works, right? So I have this on standby here. My computer is deciding not to cooperate with me very well today. If I'm able to share screen here, yeah, here we go. So this is kind of the architecture of Flux, right? So the data are in Array Lake in this ice chunk format, and then the Flux requests are being served by a serverless auto-scaling pool of workers. So they're pulling data, they're processing it, they're creating the tiles on the fly dynamically, and then your user client, whether that's in the notebook or in the web or in a desktop GIS application, just gets those tiles back. So it absolutely works with very large data sets. It's not using the local Python process to do it. Happens server side.
Okay, sounds good. Yeah, that's clear.
Yeah, I also have a question, Ryan.
Yeah, go ahead.
Yeah, thanks for the great presentation. I was wondering about the use of ice chunk. So how vital is ice chunk in your architecture, and how easy is it to implement ice chunk yourself if you already have, let's say, a cloud storage pool of source? Do you need to do something like an operation to recreate them, or can you?
No.
Yeah.
No, absolutely not. So ice chunk you can start using today, and if you have existing ZAR data, you are able to just layer ice chunk on top of that as what we would call a virtual data set. It would essentially be referencing those chunks in your original ZAR data set, but then you would start managing it through ice chunk. So this is one way you can easily sort of onboard to using this technology without having to rewrite or transcode a lot of your data. That being said, so I've been using now ice chunk, and we had a previous version of this in our earlier iteration of the platform that was proprietary, and I would never want to go back to using ZAR in the cloud without ice chunk. There's tons of benefits and basically no downsides. It's faster, it's safer and more robust to concurrent access, and it handles caching in a really elegant way. And so if you're a ZAR user today, strongly encourage you to just check out ice chunk and start using it. But one question that we are asking ourselves is, would it make sense for us to let Flux users just also use Flux with their existing ZAR data without going through ice chunk? Even though it might be less performant, there could be some issues. I'm curious, like if I told you, well, we can just plug this into your existing ZAR data without even having to go through ice chunk. Is that something that sounds interesting or useful?
Yeah, I think it does. I mean, we've also been taking a look at many of the things you are showing here, like XPublish, ice chunk, ZAR, etc., etc. So it's a very neat architecture and a very neat platform. So that would be interesting. But that's also my question: like, is ice chunk vital for the performance of Flux or not? Otherwise, yeah,
we could potentially create a version of Flux that would just use regular ZAR data. It wouldn't be as performant, and it wouldn't, the one really useful thing that ice chunk does is it tells you when a data set has been updated. With regular ZAR, there's kind of no way to know, short of like scanning the entire hierarchy and seeing if any object has been modified, right? And that makes it really hard to cache things. And so for any system like this, obviously caching is important for performance. There's various layers of caching, on disk, in memory, through a CDN, and without Ice Chunk, you just don't know what you can cache, and so the only safe thing is to just not cache things. But that may be a worthwhile trade-off for folks, and I think that's some interesting feedback. So we'll think about that, and yeah, that's useful product feedback, Giannis.
Yeah, no, thanks, Ryan. And I kind of hear from you that we should check out Ice Chunk, so I think we'll go that way.
Very cool. Alejandro.
All right. I've been following your blog post for a bit, and it's nice seeing everything put together. So thanks for the great demo. I had a question. I got a good idea there from a UI perspective on what the data catalog looks like for Array Lake, but is that just using ice chunks built in, like transactional nature, snapshots, etc., or is there something more complicated going on under the hood, like a REST catalog?
In terms of what you see in the web app?
In terms of the metadata tracking of which your commits.
Oh, you're talking about the history? Yeah, that is Ice Chunk metadata. That is Ice Chunk commit metadata. A little known capability of Ice Chunk is you can actually attach kind of arbitrary key value metadata to these commits. And so you can track all kinds of interesting things, whatever you want to track with every update, not just a text-based message. So we use that within the platform. We keep track of the user and other details about the context in which the commit came in.
So on paper, you could explore that metadata tracking or in whatever key value form you wanted, if you wanted to use it outside of Ice Chunk. And also the other question I had was, right, you showed us how to interact with Flux API, but this interacting with data without using Flux, is that just using the Ice Chunk Python library? Or?
Correct. Yep. That's the way. That's the sort of first path into the platform that I showed. Just to directly access data with Python, and there what Array Lake is doing. I'll put up this slide again to answer that question. So this is what I call direct access to raw data, opening it up directly with X-Ray ZAR. And here, what Array Lake is doing, it's helping you find the data you're looking for, through the catalog. Then it's implementing the data governance piece by saying, okay, who are you? What's your identity? Are you allowed to see this data? Do you have read access? Do you have write access? And then it's actually generating on the fly credentials, a temporary credential set for the object storage that allows you to connect directly to the Ice Chunk data in object storage. Does that answer your question?
Okay. Yeah, definitely. Thanks.
All right. Well, thanks for the questions. Happy to answer any more. Happy to hear about folks' different potential use cases, how you're managing weather data today. Really the floor is open if anyone wants to ask any other questions. Okay, we have another one from Jean. Thank you. Appreciate it.
Yeah, thanks. Just looking at this diagram, does it mean Array Lake? We only pay the computational cost on the Array Lake, and the storage cost is still just object those cloud providers, like Google Cloud, AWS, or Azure. Right?
Exactly. You asked a great question, and something I should have included probably in these slides is, how does pricing work? What's the model there? Right. So if you bring your own storage, you're already paying by volume, how many gigabytes per month. And so we don't want to double charge you for that, right? So you don't pay for the volume of storage. You pay a platform fee for Array Lake, monthly subscription fee that is proportional to, various typical software as a service factors like the number of users, the sort of type of enterprise integrations you require, support level, etc. Then Flux is usage based, and it's really based on the amount of data that gets scanned and processed by the service. And so those two different components have two different pricing models that are sort of, we think, make sense for how they work.
Okay, the data, if we have our own storage, we bring it here, there's no storage of the actual data on Array Lake.
Correct. We don't. The data can live in your cloud or in even your own on-prem object storage service. And we have customers who run their own Ceph object storage service. I will say that if you do that, there is a performance consequence, right? Because most people's on-prem object storage doesn't work quite as well as AWS S3 or Google Cloud Storage. So that's kind of a trade-off that you would have to consider in that situation. Most of our customers are just managing their own object storage buckets and connecting them to Array Lake in a mainstream cloud provider.
Okay, thanks. So one more quick question. Earlier, you showed how you import the grip data on the AWS bucket to the ZAR data. And in that particular case, where is the ZAR data stored in the end?
So that was not a virtual data set. I was just reading the GRIB data directly and writing it to directly to a new IceChunk repository. And so in that case, the data went into the bucket that was attached to that repo. So I'll just screen share here and show that part, right? So this is the repository I just created during this demo. I can see those writes that I made. If I go to the settings here, I can see the bucket for this repo is called Earthmover Production. So if I go over there and I check out the bucket, this is that bucket. It is in US East 1. We can see it's set up with the appropriate role that allows us to read and write to it and manage credentials from it. And this is our default bucket. And so Array Lake sort of orchestrated all of that. As a user, I didn't have to think about the bucket or any of those details, any credentials. It just automatically handled it for me, and my data went to the right place.
Okay, clear. Thanks. If our data is not in ZAR data format yet, we need to have some storage for the ZAR data. Yeah, got it.
No. I don't think I explained carefully. If your data is not in ZAR format, you can ingest it into ZAR format, and that's how our platform works.
And that does not incur extra cost for this storage?
No.
Okay.
But you have to pay someone for the storage.
Okay.
Probably AWS.
Okay, sounds good. Thank you. Yeah.
Okay, folks. Well, it looks like we are out of questions and running out of time on the hour. This was a ton of fun. Feel free to follow up with any questions. If you want to learn more, you know where to reach us, and we will be reaching out to you. We'll share a video of the demo. And yeah, thanks a lot for your time, and looking forward to speaking with some of you at some of our future events.